If dark matter is collisionless even with itself, how will you detect it using detectors that look for collisions? It's a great and troubling question, and one we must reckon with very seriously. Here's what the science has to say about it. Observationally, there's an overwhelming amount of evidence that indicates the presence of a species of energy that has existed from very early times in the universe's history, that gravitates like the matter we're familiar with does, but that shows no evidence for interacting in any other way, either with itself or with any of the known particles of the standard model. We see evidence for the presence of this unfamiliar material, which serves as a source of gravity across a wide variety of cosmic probes. It shows up when we weigh individual galaxies, when we weigh pairs of galaxies that are interacting, when we measure the gravitational lensing effects of galaxies, galaxy groups, or clusters of galaxies, when we tally up the total amount of normal matter in stars, gas, dust, plasma, and black holes, and compare it with the total mass that we see in a variety of cosmic objects. When we examine the pattern of fluctuations present in the CMB, the leftover glow from the Big Bang, when we examine the clustering patterns imprinted in the cosmic web, and when we measure a feature known as baryon acoustic oscillations imprinted in galaxy-galaxy correlations across hundreds of millions of light years. All of these independently measurable lines of evidence indicates that the normal matter we see is wholly insufficient to explain the universe we observe on its own. Something else in addition must be present. Early on in the crucible of the Big Bang, temperatures were high enough and densities were great enough that nuclear reactions could proceed, where protons and neutrons would undergo fusion reactions, creating a variety of light elements and their isotopes in some non-negligible abundance. The nuclear physics that took place in the very early universe, known today as Big Bang nucleosynthesis, is extraordinary because all of the reactions that occur, leaving behind a specific abundance of these various elements and isotopes relative to one another, is dependent only on one cosmological parameter, the baryon to photon ratio. We've since measured that value exquisitely and found that it's about 6 × 10⁻⁻10, meaning there's about one baryon, proton or neutron, for every 1.7 billion photons in the universe. That corresponds to a matter density that's about 5% of the overall density of the universe, but measurements of the total amount of matter in the universe from galaxy clusters and gravitational lensing observations, for instance, reveal a figure that's more like 30% of the universe's total energy density. All of these lines of evidence, when put together, clearly indicate the presence of some type of mass in the universe that isn't part of our standard model. Moreover, that mass has to have specific properties that are highly constrained by cosmic observables. It must have existed from very early times, as its signals are thoroughly imprinted in the CMB. If it was created thermally, it was heavy enough that at no point in cosmic history was it moving fast relative to the speed of light. It must not have annihilated away with itself, must not have clumped together like normal matter does, and must not have interacted electromagnetically, through the strong force, or through the weak interactions in any appreciable, measurable way, even from early times. For these reasons, what was originally referred to as the missing mass problem became known as the dark matter problem, as it appeared that the universe must contain some type of massive species of energy that gravitates, but that doesn't emit or absorb light, and doesn't interact or collide with normal matter or itself in any detectable way. Beginning in the mid-2000s, we started to even detect clear signatures that some type of massive signature must be present within galaxies and galaxy clusters, as colliding systems began to reveal a clear separation between the normal matter, which heats up and emits X-rays, and the total mass, which is revealed from gravitational lensing signals. The evidence from the full suite of evidence strongly indicates the presence of a massive new species of energy, which experiences the force of gravity and clumps together on cosmic scales, but which doesn't splat together, interact with light, or make bound structures with either normal matter or itself in any discernible way. So what could this dark matter be, and how could we detect it? There are two main ideas that have been pursued since the latter half of the 20th century. Dark matter could be WIMP-like, meaning that there could have been a massive, heavy particle beyond the standard model that was once produced in great abundances in the early stages of the hot Big Bang. As the universe cooled, Some species of massive relic particle persisted, moving slowly compared to the speed of light, and it still persists today. Although rare, interactions and collisions with standard model particles could still occur, since that's how these particles at very high energies were created in the first place. Dark matter could also be axion-like, in the sense that it could be made of particles of any mass, not just heavy ones, that were pulled out of the quantum vacuum during a phase transition in the early universe, but that were born cold, with practically no kinetic energy at all. The hypothesized Pettier-Quinn symmetry and the breaking of that symmetry was the origin of the Axions as dark matter idea and of this mechanism. Even though that idea in its original incarnation has now been ruled out, the search for axions and axion-like particles continues. The way you search for WIMP-like particles is to build experiments that look for nuclear recoils, as there should be some non-zero cross-section, at least at some high energy, and presumably at lower energies too, between whatever dark matter is and at least one of the standard model particles. Complementarily, the way you search for axion-like particles is to build an electromagnetic cavity that's capable of exploiting a theoretical coupling between axions, or axion-like particles, and photons. At low temperatures and when tuned to specific frequencies, any dark matter particles that happen to be passing through the detectors, dependent on their mass and cross-section, could be converted into photons, and detecting those photons would then be a telltale signature of dark matter. But here's the thing. Dark matter doesn't have to be a thermal relic that arose from interactions with standard model particles, and it doesn't have to be a pulled from the vacuum relic that will couple to the photon or any other standard model particle. It could be a heavy, exotic, right-handed neutrino that was created at the start of the hot Big Bang and never interacts with anything in the standard model, an ultra-heavy WIMPzilla particle that was created early on through purely gravitational processes, and will never interact with any standard model particle through any force or something more general that arose from a severely out of equilibrium condition, which wouldn't necessarily interact with any of the standard model particles or fields through the strong, electromagnetic or weak interactions. If any of these are the case, then all our current classes of experiment will do is continue to push down to lower and lower boundaries, the cross-section of whatever dark matter is in a certain mass range below a certain limit. This is an incredible feat of experimental physics, but it isn't ever going to reveal dark matter's nature directly if this is the case. A lot of people think that because we talk about dark matter as possibly being made up of WIMPs, where WIMP stands for weakly interacting massive particle, that we fully expect it to interact through the weak interaction. This is not true. There is a scenario known as the WIMP miracle, where if you make a thermal relic in, say, supersymmetric or similar scenarios, the cross-section you need to produce the right abundance of massive particles to match observations just happens to match the predicted cross-sections that would proceed through the weak interactions. However, as LHC data is more and more convincingly showing, the parameter space for the WIMP miracle scenario is almost entirely excluded. The WIMP miracle, except among the most fervent supersymmetry believers, is almost totally dead. Instead, I think it's worth recognizing that what we would have once considered a nightmare scenario for dark matter, the possibility that it has no interactions to observe other than gravitational ones, might in fact be the scenario that nature has presented us with. The theoretical motivation for completely collisionless dark matter is very strong, as there are no signals indicating collisions with atomic nuclei, no signals indicating conversion to photons, and no signals indicating a self-interaction or self-annihilation cross-section, and yet the observational evidence indicating dark matter's presence is overwhelming. This is not a flaw or a fault in our techniques. This is a limitation imposed by what the universe gives us to work with. It is only normal standard model particles that we know how to interact with. If we think more generically, any species of energy that strikes a particle, a quark, a gluon, an electron, etc., is going to impart energy and momentum to it whenever it occurs. We can build enormous detectors around collections of matter, things made of quarks, gluons, and electrons, and look for any of the downstream signatures that are generated by such a collision. The goal shouldn't be to find dark matter, as that's assuming we know what nature is up to, and that is not a thing we're able to know until we find out. The goal should be to interrogate nature as comprehensively as possible, and to put as many well-motivated or even not ruled out scenarios to the critical test as possible. The push to make experiments that take larger, more pristine samples of material and observe them for longer periods of time with well-accounted-for backgrounds and ever tinier uncertainties and errors is literally the best we can do with the universe we have. While there are many prominent voices who fail to see the scientific value in this, the only alternative is to throw our hands up in the air and give up before even making the attempt. Whenever we're in the realm of the unknown, venturing beyond the frontiers of present-day knowledge, we are compelled to both maximize our discovery potential while simultaneously making sure we don't fall victim to wishful thinking and finding something phantasmal that conforms to our hopes and expectations. This approach to fundamental science has brought us to where we are today and continues to help us probe the nature of reality at an elementary level to better precision than ever before. Yes, if dark matter is truly collisionless, these experiments we're conducting and planning and building will not reveal its nature. But science is a cumulative endeavor, and every step we take along the path has valuable lessons to teach us, if only we're willing to learn from what nature reveals about itself. Thank you so much for coming this far with us. See you soon again the next day in the next video. Until then, good night, and remember to dream big.